All right, ladies and gentlemen, today we are going to learn something really cool, and that is simplifying expressions with the quotient rule and also working with square roots. These roots are a really fun game that you can play. They look hard, but if you know the rules, it becomes like a game, all right? And that is in fact most of math. It's a game. But it is important that we know the rules of the game. Let's take the problems one at a time and we'll learn the rules as we go. Here's number 1. We are given negative 30a over 50a squared. Okay? So we need to know the quotient rule in order to work with this. The quotient rule says, here's the quotient rule. You can also call this rule the division rule for exponents. The quotient rule says when you have exponents in the numerator and denominator for variables that are the same, you subtract the exponents. So we'll say this: when bases are the same, I'll move my hand. When bases are the same, subtract the exponents. Okay, so that's the rule that we need right now. We have here a base called A. Here's another base A, all right? So it says that we should subtract the exponents, but for A by itself, I don't see an exponent. Well, good news is there's really one there, and it's that elusive exponent 1. All right, so whenever you see a letter just hanging out by itself, it's understood that there's an exponent of 1. So here's how I would like to write this. We're going to rewrite this as negative 30 over 50 times A raised to the power of 1 minus 2. You see what I did there? So you have 1 in the numerator, 2 in the denominator. So we subtract 2 from 1, and we'll continue to simplify that. What is that? Well, that is just negative 30 over 50 times A to the negative 1 power. Okay, so here's another rule. So this is a rule that we need to work with, the negative exponent rule. Remember, these are just rules of the game. I mean, it's no different than football. It's like down by contact, okay? Or rules about pass interference or face mask grabbing. As long as you know the rules of the game, you can play the game. Here is the negative exponent rule. Okay, didn't quite get that centered. Whatever. Here's the negative exponent rule. When you have a negative exponent, like negative 1, it can be rewritten as 1 over the letter raised to the same exponent but positive. So just look at it for a second, it becomes apparent. If you end up with a to the negative 1, you rewrite it as 1 over a to the first power. Okay? So that's our negative exponent rule. And it works the same way in reverse. If you find yourself with 1 over a, okay, you can rewrite that as a to the negative first power. That's the negative exponent rule. Works both ways. Well, over here we're presented with case 1. So we're going to write this again as negative 30 over 50 times 1 over a. Remember, there's that little 1 in the exponent section. And we just apply the negative exponent rule there. We applied the quotient rule here and negative exponent rule here. We can continue to simplify this by reducing this fraction. Right away, I can see that I can cancel the zeros by dividing top and bottom by 10. Okay, so in this case, the GCF was 10, and that means I can divide a 10 out of the numerator and denominator. So here's the next to final step. We've got negative 3/5 times 1 over a. And we're just going to do one final step to fully simplify this. Let's just multiply these back together, multiply across. Negative 3 times 1 is negative 3. 5 times a is 5a. Okay, so this is the answer, or the simplification. And the key thing to remember with simplification is that this complex expression is equal to this simpler expression. And that's the whole point. Okay? So now, let's do another one. Number 2. We are given 48 n squared over 42 n. Okay, so the first step here I would like to do is to kind of break this fraction up. We can break it up into the number part, 48 over 42, times the variable part, n squared over n. Remember, it's n to the first power. So now we'll apply the quotient rule. Okay, so that is equal to 48 over 42 times n to the 2 minus 1. Okay, remember quotient rule, subtract, when the bases are the same, they're both n, we subtract the exponent for the variable in the denominator from the exponent for the variable in the numerator. It's just 2 minus 1, right? So what is 2 minus 1? It's just 1. So we'll rewrite 48 over 42 times n. Okay, we could say n to the first power, but n to the first power is just n. So let me just write this so you can see it. N to the power of 1 equals n. All right, so we just write n. We're trying to make it simpler. All right, time to reduce this fraction. We need to find the GCF of 48 and 42. What is the GCF for 48 and 42? Well, Who knows, right? I mean, we could sit here and guess, but there's a foolproof way to find it, and that is to prime factor. We'll take 48 and 42. Some of you are not going to do this because you're going to figure it out just in your own head using tables, and that's fine for this problem, good for you, but for other problems, no. You won't be able to think of the factor. All right, so 48 is an even number. Let's divide by 2. That's the smallest prime number that we can use. And let's remember as we do this, our prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and that should probably be enough for now. All right, so what times 2 equals 48, or what is 48 divided by 2? It's just 24. Let's break down 24 into 2 times 12. Let's break down 12 into 2, 6. And we'll break down 6 into 2 and 3. Similarly, let's break down 42. Okay, 42 is even, so the first factor is always 2 when it's an even number. And what times 2 equals 42? That's 21. Let's break down 21 into 3 and 7. All right, so here's what I'd like to do. Let's find in both prime factors that are shared, okay? What do I mean by that? I want to be really clear about what I mean. I'll play the game, and then you play it with me. I spy a pair of 2s. There's a pair of 2s. So as part of my GCF, I'll put 2. Just watch. Now I spy a pair of 3s. Okay, so 2 times 3. I don't see any other pairs here. Okay, so the GCF is 2 times 3, greatest common factor. 2 times 3 is 6. What do I use a 6? Well, that means I can divide a 6 out of 48 and a 6 out of 42 and be sure, because I've used prime factoring, that I'm simplifying this fraction as much as possible. So we will divide both the top and the bottom by 6. All right, so let's write the next step. This equals 48 divided by 6, 8, over 42 divided by 6, which is 7, times n. So now we'll recombine. Remember, n can be written as n over 1. You can do that with any number or letter that's just by itself. So if n is really n over 1, I can multiply across the top and across the bottom. Let me just make it super clear. I don't want anyone to feel left behind on this one. 8 over 7 times n over 1. Okay, so I'm now going to multiply across the top and across the bottom. 8 times n is 8n. Over 7 times 1 is just 7. And there's your simplified answer. Okay? So the next two problems, number 3 and 4, are solved in exactly the same way as numbers 1 and 2. So I think I'll leave those for you to do. So I don't want to give away the whole game here. Let's see what's coming up next. So I think we switch concepts now. Yes. So we're going to simplify these radicals, okay? Just square roots. The process is almost identical, but there's some cool square root stuff we're going to learn. All right, so I'll do number 5, and then y'all can do number 6. Number 5, we are given square root 36 k to the 4th power, and we're asked to simplify it, right? Prime factoring is the name of the game. Okay, prime factoring is the name of the game. What we have to do is prime factor 36 and also prime factor k to the 4th power. It might seem weird to prime factor that, but it's actually, this is easier than this. All right, 36 is an even number, so we start with 2. What times 2 equals 36? It's 18. Still even, so we'll break that down. 18 divided by 2 is 9. And finally, break that down, 3 and 3. Now, k to the 4th. So this is how this works. K to the 4th is k times k to the 3rd. Break it down again. You've got k times k to the 2nd. Break it down again. You've got k times k. All right, it seems a little weird. What does this really mean? K to the 4th power is just k times k times k times k. You just write k 4 times. K to the 4th power is k times k times k times k. You use the product rule to verify that. Each one of these has a little exponent of 1. When you multiply bases that are the same, you add the exponents. So this is just k to the 1 plus 1 plus 1 plus 1. And that is k to the 4th. All right, so I just broke it down into k's. Here, I broke down 36 into prime numbers. Same process, all right? So now, what we're going to do is rewrite this with a big square root so we can fit all this under the square root. I think I'll actually do it down here. No, I'll move it over. Here, I'll write square root, and then I'm going to put a long square root bar like that. Don't worry, it's not scarier. It's just, instead of writing 36, I'll write the product of the primes. 2 times 2 times 3 times 3. And instead of writing k to the 4th, I'll write times k times k times k times k. All right? Now this is that step where we think we've made it worse, but we haven't. Okay, we haven't. We're on the verge of making it very easy. Here's the key thing to remember. The square root is really the second root. We just don't write the 2. Okay, so there's a little 2 there, and that's called the index value. It can be anything. Okay, starts with 2 and it goes up 3, 4, 5, whatever. This is the index value. And here's the cool thing about the rule. If you have 2 numbers inside, like this, they can be rewritten. Let's just take 2 times 2. 2 times 2 is equal, think about it this way. They both have exponents of 1, so it's equal to 2 squared. Okay? So, if I have the second root of 2 squared, that can be rewritten as 2. Okay, because I'm taking the square root of 2 squared. So here's the key. Whenever this index value matches the exponent, the root symbol, the radical sign, disappears. Okay, that's the rule. I mean, it's a neat little game. So now we're going to play another little game. We are going to group our pairs of numbers or letters. So here I spy a group of 2's, and that group of 2's can be rewritten as 2 squared. Here's a pair of 3's. That pair can be written as 3 squared. Here's a pair of k's. That can be written as k squared. Here's another pair of k's. That can be written as k squared. So we're going to rewrite this. Remember, this is the second root, square root, the second root. Instead of writing 2 times 2, I'll write 2 squared times. Instead of writing 3 times 3, I'll write 3 squared times. Instead of writing k times k, I'll write k squared times. Instead of writing k times k, I'll write k squared, and we're done. Okay? So here's one final rule. When I've got terms like that, I'll just take 2 of those to demonstrate the point. If I've got the second or square root of 2 squared times 3 squared, I can break it up. Whenever I've got multiplication, I can break this up into 2 separate square roots, like this. That is equal to the square root of 2 squared times the square root of 3 squared. Okay, make sure you pay attention to that. So we just break it up. Everywhere we see a dot, we're going to break it up. So here we're going to break this up into 4 separate roots, and y'all like how this turns out. So this is equal to, should be writing equal to. This is equal to the square root of 2 squared times the square root of 3 squared times the square root of k squared times the square root of k squared. Okay. Remember, there are 2's that are not written here. This is index value 2. So look what we have. Remember our rule. If these two match, if the index matches the exponent, you can just get rid of everything but this base here. So this whole mess becomes 2 when you have those things. Well, check it out. We have matching indexes or indices and exponents in each term. See this? They all match. So that means that this guy right here just becomes 2. This square root 3 squared just becomes 3. We multiply them together. The square root of k squared just becomes k. And the square root of k squared just becomes k. All right? And those are all multiplied together. So we have just simplified this where we've gotten rid of all the square roots. Well, now we'll multiply back together because we're done. We just have to make this look prettier. 2 times 3 is 6. K times K, here we're using the product rule of exponents. K times K is K squared. So we write 6K squared. And that is the simplified expression. Pretty elegant, right? It's pretty neat that we can do that. Take square root of 36k to the fourth and get rid of the root entirely and leave just 6k squared. So I'll let you do 175p. All you're going to do is prime factor 175, right? Remember your rule. You add these digits up. 1 plus 7 is 8. 8 plus 5 is 13. That's not divisible by 3. So your prime factor is not going to be 2 because it's an odd number. It's not going to be 3 because 175 isn't divisible by 3. So I would start by factoring on your tree, where you write the little tree legs. The first and smallest prime factor is 5. So you'll divide 175 by 5 and continue to break it down. Shouldn't be too hard. Here's the final part of this. Let's take number 7. Okay, number 7, we are given 7 square root 36x over square root 21x. And I want to make sure it's clear that the x is underneath the square root symbol here. Like that. Okay? And we got to get rid of this. We got to simplify it. We got to work with it. You need to know a couple of rules. Here's one rule. The square root of 36x can be rewritten as 36x, all of it, raised to the 1/2 power. Okay? This 2 comes from the index, and this was a little 2 here. And the 1 comes from the fact that this radicand, or the stuff underneath the square root, is all just raised to the first power. Okay, so the 1 comes from there, and the 2 comes from there. So that's how the square root of 36x can be rewritten as 36x to the 1/2. Okay, here's one more piece, right? You've got square root 21x in the denominator. So let's imagine that we've got 1 over the square root of 21x. That can be rewritten as 1 over 21x, all raised to the 1/2 power. And using our negative exponent rule, we'll apply this case here, okay, right here. We have something in the denominator, and we can rewrite that as that raised to the power of -1. All right, so here the power is 1/2. So we can rewrite this as 21x raised to the -1/2 power. Okay? So we've got all the hardware we need to do number 7. So we're going to break down 36 and also break down 21. .36, well, it's even, so the first prime factor is 2. 2 times 18. Then we'll break down 18 to 2 times 9. Break down 9 to 3 times 3. I can already see here that I can write, I got a pair of 2's and a pair of 3's. I can rewrite this as 2 squared times 3 squared. Okay, so I'll use that. Now 21 is just 3 times 7. So that can't be broken down any further. Let's now rewrite this as 7 times the square root of 2 squared times 3 squared times x. All that's under the square root over the square root of 3 times 7. Okay? So remember, we're going to now break these roots up just like we did up here. So this is equal to 7 times the square root of 2 squared times the square root of 3 squared times the square root of x, all over the square root of 3 times the square root of 7. Okay? And I drop the x. Here there was an x times x. Right? Here it's times the square root of x. Right, so we're getting to where we're going to be canceling some stuff. Notice that I've got a square root of x over a square root of x. So those can cancel. Okay, those are gone now. And I've got index values that match the exponents here and here. So this can just become 2 and this can just become 3. So we'll simplify 7 times 2 times 3. Okay, over the square root of 3 times the square root of 7. Remember, we can rewrite square roots as something raised to the 1/2 power. Okay, so we will write, again, 7 times 2 times 3 over 3 to the 1/2 power times 7 to the 1/2 power. And then we will remember that if we have something to the 1/2 power in the denominator, it can be written as negative 1/2 power in the numerator. So now I've got 7 times 2 times 3 times 3 to the negative 1/2 power times 7 to the negative 1/2 power. So now we're going to group, let's remember, these are all 1's here, and 1 can be rewritten as 2 over 2. So let me rewrite this as 7 to the 2/2 power, which is just 1. And I'm going to put this one over here next to it, times 7 to the 1/2 power times 3 to the 2/2 power times 3 to the negative 1/2 power. Yeah, that should have been negative 1/2. Negative 1/2 power times, the only thing left is 2. And now we just use the product rule to add the exponents. So here this is 7 to the 2 minus 1 over 2. That's just 7 to the 1/2 power times 3 to the 1/2 power times 2. Remember, anything raised to the 1/2 power is just the square root. So I've got here square root of 7 times square root of 3 times 2. All right? And remember, when we have square roots, those can be combined. We broke them up before. Well, now we'll recombine them. The square root of 7 times the square root of 3 is just the square root of 7 times 3, and all that times 2. So 7 times 3 is 21. We'll bring this 2 up front to make it look the way it's supposed to look. We have 2 times the square root of 21. And that is the final simplified form of this expression. And I think this is really cool because we went from 7 square root 36x over square root 21x to having no square roots, no denominator with square roots and no x's. Pretty neat. Okay, so there's 4 of those like that. All right, guys. Well, I hope this video was helpful. I think you guys will get this really well with practice. You'll be able to do it. Okay. Please give this video a like if it was helpful to you. If you have a question, please leave it in the comments section. And if you have not already, please subscribe and hit that notification bell so you're always alerted to new videos on this channel. Thank you.